Okay, we should be live at some stage. Should be live at some stage. What's the delay like? Should be live at some stage. Okay, so everything we do is available on BioniChaos.com. Go check it out. Provide your feedback. That's the usual spiel. I don't know how many times I repeated it already. Too many times. Let's do something real quick. So we're using Gemini. A lot of Google products, whatever, Google services. Okay, so we use it like in two different ways. I'm not going to show it to you, I don't know, for copyright reasons or whatever. Google doesn't really pay me. I mean, if they want to sponsor this, they're more than welcome to. Anyway, we created I can hear my own voice, which is not good. I'll mute that. Okay, so we created a notebook LM, and we're gonna talk about pacemakers. So it's also called the cardiac resynchronization therapy. Don't try repeating that at home. You'll break your mouth. But the most interesting thing is that we have this prompt. We gave it to two models to essentially make a simulation out of this topic. So we gave it to Gemini 3.5 Flash, and Gemini 3.1 Pro Preview, whatever the model names are, no one really cares. But they both generated code. And as you know, we like code. We'll give it a name. We'll have to, we'll call the pacemaker, because that's a good name. It's a good little name. We'll start a new folder. It doesn't matter which IDE we are using. No one cares about that, I think. We'll add the HTML. So I'm doing JavaScript only at the moment. But again, no one cares. Index HTML. Only care if the thing works or not. And we'll have a copy of it. And which models should be better? So in theory, even though 3.5 is a more recent model, but 3.1 Pro, I don't know what the benchmarks are. I'm not going to check the benchmarks. Interestingly, can preview them in the browser. But we're not going to do that because we need it to work well first locally, then on our server, so we make it available on BioniChaos.com. Okay, one of them is 822 lines, and the other one, gel model, is far more than 1,000 lines. Okay, so the new model, the Gemini 3.5 Flash, is less lazy. But the question really, does the code make any sense? So let's test the short code first. We'll run it locally. Okay, and we have a pacemaker simulation. It actually looks pretty decent. I did try stuff like this a while back. Okay, it has a nice notification to it. It says the heart pumping. I like the sound. Pacemaker on. Wait, that was the pacemaker off. That was doing 75 beats per minute. Pacemaker on. And it's doing the same. Why the visualization doesn't indicate if it's okay? So if it's off, there's that green LED light on the pacemaker itself. Whether you're meant to see it like through your abdomen or something, through your skin, surely not. When you turn it on, pacemaker on. Okay, so the rhythm is normal. Okay, so if we turn it off and we have a heart block, I'm having a heart block, and then turn the stimulator on. It's doing V pacing, and my heart rate is back to 75 BPM. How good this simulation is! It's pretty amazing. And this one was done by, now I forgot which model is which. Gemini 3. Well, we're using Gemini 3.5 Flash and Gemini 3.1 Pro, whatever. We have two versions of it. Let's turn the sonification off for a sec. We'll check the second version. And yes, we ask for some description at the bottom. Blue sparks. Watch the blue sparks indicating the device is delivering an electrical pacing. Are there blue sparks? I didn't see any blue sparks. Blue sparks. Is that the spark? What? Okay, the sparks are off. That meant with the spark? Okay. Bradycardia. Whatever that does, it will do a simulation of it. Very nice. 37 beats per minute. Almost dying, am I? And then we turn the pacemaker on. Yeah, it does some sort of spark. Still like a spark between the device and the heart. Those meant to be the electrodes. Yeah, the spark meant to be just coming outside the electrode, wouldn't it? Or between the two electrodes. It's not meant to be coming from the device to the heart. That's what the electrodes are for. Or am I missing something? Am I missing something? I don't know. Okay, we'll go back to normal rhythm for a sec. Pacemaker off, sonification off. Okay. Okay, let's see. We have a now version of the code, and then we also have a notebook level review of how pacemakers work. So that will make a great content. There you go. I can replace a university course on pacemakers. Can you? What do you think? Write in the comments. Okay, we had another version. We already copied it. Yes, we are like in I forget, Visual Studio Code, whatever. And we had version 1, index 1, and we have a copy. This one is a longer code. We'll run that locally as well. Eventually we'll make it available for you. Okay, this one is much more, okay, wait a second. This one's much more comprehensive. It's much more comprehensive. Dual chamber. Intrinsic rate, what? Poof. Yeah, obviously so interestingly enough, we had two models generating two pieces of code. I suspect this one was done by Gemini by the Pro version. Was this the Pro version? Not sure. I suspect it will be doing something more comprehensive. We can indicate which version is which. We don't mind doing that. No, actually, the simpler simulation was done by the Gemini Pro version. Interestingly enough. And the more complicated stuff was done by Gemini 3.5 Flash, which meant to be a quicker model. So not sure what to make of that. Not sure. Anyway, we have an explanation as well of how pacemakers work. So listen to that and go from there. Yeah, everything we do eventually goes on to BioniChaos.com, so check it out, provide your feedback, like, subscribe. We're almost at 2,000 subscribers, so you know what to do if you want to help out. And let's just do Notebook LM unless there's any questions. So there is a human in the loop, just if you were wondering. We can try and answer things ourselves. We might we'll ask while we play the audio. We actually can do it in interactive mode. Sometimes the interactive mode is not available. So this is Notebook LM, interactive mode, overview of some literature on how pacemakers work. So it should be fairly basic stuff, and we will do it while watching this. Should publish them straight away. I think they're ready. They're ready to be published. Well, mainly we're publishing so you can actually try yourself whatever we are doing, whatever we are working on. So I don't know if we need to decide if we're keeping both versions or just the one. Ideally, we don't want to mess around with the code. How much did it take in the 37, 39? Yeah, so they're pretty efficient. Yeah, ideally we could have done something like where you have a more basic model and then you have more basic simulation and then you click a button and it gives you a more comprehensive version of it. Because obviously this one has way more stuff going on for it. And obviously no one reads any text. Yeah, we kind of like single. Yeah, the big advantage of this one is that it's a single page. Everything is in the one viewport. This one you had this scroll button for the settings. And I don't know how it will look like on mobile. It will probably be horrendous. Pacemaker cardiac conduction simulation. Dual chamber model. So I don't know if it's even accurate or not. Because, yeah. Anyway, let's do the Notebook LM overview and we'll go from there. We'll do it in interactive mode so I can comment along or whatever. I mean, I can pause it and comment along. Is it starting 2 hosts? How cardiac pacemakers power the heart? Oh, actually I had to press a button.
You know, we take the power grid completely for granted. I mean, you walk into a room, you flip a switch, and the lights just come on.
Right. It's just always there.
Exactly. There is this invisible, relentless flow of electricity making your entire life possible. And you really don't think about it until, well, suddenly there's a storm.
Yeah, and the lights flicker.
Right. The fridge hums down to silence, and you are left sitting in the dark, realizing just how dependent you are on that continuous current. Now, imagine that same scenario, but instead of your house, it is your own biology.
I mean, that is a really visceral way to look at it. What we tend to think of the human body purely in terms of, plumbing and mechanics, blood flowing, muscles pulling.
Yeah.
But the foundation of all that movement is electrical.
And today, we are taking a deep dive into the ultimate biological electrical grid, specifically the human heart. We're looking at what happens when that natural grid starts to fail, and medical engineering steps in to install a backup generator.
Which is an incredible feat of engineering, really.
It totally is. So we are talking about cardiac pacemakers today. And to do this, we've gone through a foundational medical textbook on pacing, alongside some incredibly detailed clinical overviews from the Mayo Clinic, the NIH, and WebMD. Plus, we've got a really grounded patient guide from Melbourne Heart Rhythm to help us understand what it actually feels like to live with one of these devices.
That patient perspective is crucial, yeah.
Okay, let's unpack this. Because before we can really understand how a machine fixes the heart, we have to understand how the heart's natural wiring is supposed to work in the first place.
We really do need to start with the original equipment. The entire sequence of the heartbeat, that coordinated squeeze that pushes blood through your body, it's triggered by a tiny internally generated electrical spark.
Like a liberal spark.
Basically, yeah. And that signal starts at a location called the sinoatrial node, or the SA node.
So kind of like the master switch on the breaker panel.
That's a great way to look at it, actually. The medical text describes the SA node as being located at the, and I'm quoting here, the superior aspect of the crista terminalis.
Which
Someone is saying
means
it's a
absolutely
cool
nothing
simulation.
to most
Yeah,
of us.
it's thanks
Fair
to
enough.
Gemini.
To translate that, just picture a microscopic cluster of highly specialized cells sitting right up near the ceiling of the heart's upper right chamber.
Okay, up near the ceiling.
Right. It's positioned strategically exactly where the main vein brings oxygen-depleted blood back from the body. This little cluster of tissue is basically a biological battery that spontaneously generates an electrical impulse.
So the master switch flips at the top of the heart, but how does that current actually travel through the house to get the whole muscle to squeeze? I mean, it can't just be a random shock, right?
No, it is a highly choreographed pathway. The impulse fires from the SA node, and it ripples through the muscular walls of the upper chambers, the atria, causing them to contract and push blood downwards.
Okay.
Then, the electrical signal hits this crucial choke point called the atrioventricular node, or the AV node.
Wait, why a choke point? Wouldn't you want the signal to move, like, as fast as possible?
Well, you'd think so, but the AV node is normally the only electrical connection between the top and bottom halves of the heart, and its primary job is actually to slow the signal down.
Huh.
It acts kind of like a red light at an intersection. It holds the electrical charge for just a fraction of a second. This delay is physically necessary because it gives the lower chambers, the ventricles, time to completely fill up with the blood that was just pushed down from the top.
Oh, wow, that makes perfect sense. If the top and bottom squeeze at the exact same time, they'd just be fighting each other.
Exactly, they just clash. Once the lower chambers are full, the AV node turns green, so to speak. It releases the current, sending it rushing down into a specialized transit network called the His-Purkinje system.
The His-Purkinje system.
Right. These are basically high-speed biological wires embedded in the walls of the lower chambers. They distribute the electrical signal.
Yeah, so wait a sec. Oh, am I? Can I continue from this?
Instantly across the heavy muscle of...
Yeah, this one is sending the pulse. So the one major problem, seemingly, I don't know if it's intentional or not, but sending a pulse directly from the device. That's that spark there. So you can turn. Sorry, the sonification is too loud, is it? There's no loudness control to this thing, but not in the browser. But so when you turn the pacemaker on, yeah, it's supposedly stabilizing Let's review it. Turn the signification. So you have the normal rhythm, which is okay, 75. Then you have bradycardia. So the rhythm drops, heart rate drops to 37. And you have this weird activation, whatever. And then we turn the pacemaker on. It's sending the pulses, whatever, those sparks. Even though, aren't they meant to be coming through the electrode? I don't know why they're coming from the device. What's that bit on the device? Yeah, not sure. And then it will go forever, would it? Wait, and what happens if you have normal? Okay, so when we have a normal heart rate and the pacemaker is turned on, it's actually not stimulating, which is what you would expect, wouldn't you? Would you? This was actually Gemini 3.1 Pro that made actually, interestingly enough, a more simple visualization. So I'm not sure how do you go about following up. We have it in compare mode. So I don't think we can follow up, and I'm not sure. Wait, let's turn the signification off. The other one, does the other one have signification? Sensing only. Yeah, obviously this one's more complicated. I don't know if it's accurate. Can anyone tell me if it's accurate or not? I don't know what's up with the controls. Like they're not very. So you have a block. Okay, we have a block. And then we have whatever stimulation that meant to fix it. And it was automated, was it? It's the stimulation. Trigger. I don't know. It's too complicated for my understanding.
The ventricles, and that causes a massive, forceful contraction that blasts blood out to your lung and the rest of your body.
That is just the perfect biological scenario. The switch flips, the traffic light delays it just long enough, and the high-speed wires trigger the main pump. But, biology degrades over time. Things break. What actually happens when this wiring gets faulty?
Well, a lot of different things can disrupt the grid. As we age, scar tissue can build up in the heart.
Like frayed wires.
Sort of, yeah. Or sometimes a heart attack damages the natural pathways, or a patient might just have a genetic predisposition for it. The SA node might start generating a spark too slowly, or it might fire irregular load. Or that crucial AV node, the traffic light we talked about, might get stuck on red, completely blocking the signal from reaching the lower chambers.
Which means the main pump isn't getting the memo to squeeze it all.
Yes, and the result is a dangerously slow or irregular heartbeat. You just aren't circulating enough oxygen-rich blood, which leads to extreme fatigue, lightheadedness, or even sudden fainting spells.
And I guess that is where the artificial pacemaker comes in. Now, I've always wondered how you introduce a machine into an existing biological circuit without them just, fighting each other for control.
What's fascinating here is that the artificial device exploits a natural biological loophole.
Really, a loophole.
Yeah. The heart's natural pacemaker, the SA node, is only in charge because it's the fastest. It operates purely on speed. The tissue that depolarizes or fires at the fastest rate automatically becomes the dominant pacemaker for the whole heart.
Okay, it's a speed thing.
Exactly. But the SA node will actually suppress its own activity if it detects a rhythm that is even slightly faster or more consistent than its own.
Wait, so the machine essentially walks in, taps a slightly steadier beat, and the biological node just steps back and says, okay, you're the boss.
That's exactly the mechanism. Medical engineering just takes advantage of the heart's natural hierarchy.
That is so wild. Let's talk about the actual hardware making this happen. The Melbourne Heart Rhythm Patient Guide gave me a totally different mental image than I had going into this.
What were you picturing?
I don't know, something clucky. But a traditional pacemaker basically has two main components. First, there's the pulse generator, which is a small, sealed titanium disc that holds the lithium battery and the microcomputer.
Right, the brains.
Exactly. And then you have the leads.
The leads are the physical wires that route the electricity from the generator down into the heart tissue.
And the patient guide describes these leads as being soft, insulated cables about the diameter of a spaghetti noodle.
It is a really good visual.
It's such a strange but vivid way to picture it. You have a titanium disc and a couple of spaghetti noodles. But this brings up a massive question for me. If I have a wire stitched into my heart muscle, is it just constantly zapping me 20/47? Like a metronome I can never turn off?
Oh, that is probably the most common misconception. Modern pacemakers are not metronomes. They are what we call demand pacemakers. They're constantly performing two very distinct actions, pacing and sensing.
Okay, pacing, I understand. That's the zap. But sensing, how does a piece of titanium wire sense a biological heartbeat?
Well, the heart's natural electrical signal is essentially a tiny shift in voltage. We are talking about millivolts here. The metal tip of the pacemaker lead acts like a highly sensitive microscopic voltmeter. It is constantly listening to the ambient electrical field of your heart muscle.
So it's just sitting there waiting for a voltage spike.
Yes, exactly. The computer is programmed with a specific threshold. Let's say it's looking for a natural heartbeat at a rate of 60 beats per minute.
Okay?
The wire listens. If your heart fires a natural electrical impulse, the wire senses that voltage, reports it to the generator, and the generator does absolutely nothing.
Nothing at all.
Right? It just resets its timer. It will never override a healthy natural beat.
It just sits on the bench.
Yep. But if the timer picks down and the wire senses that the natural voltage hasn't happened, then it delivers a tiny electrical pulse, usually just 1 or 2 volts down the wire to trigger the muscle. It only kicks in on demand.
It's essentially a safety net. It only catches you if you fall. That really changes the way of think about living with one. But, fixing a slow heartbeat is just addressing speed. The materials we looked at get into something a bit heavy, which is heart failure.
Right?
What if the problem isn't the speed of the beat, but the physical coordination of the muscle?
That moves us from simple electrical repair into complex system optimization. Heart failure is a condition where the heart is working incredibly inefficiently, and often this is because the two lower chambers, the right and left ventricles, have fallen completely out of sync.
I was reading about the mechanics of this, and it completely shifted my understanding. The right and left ventricles are supposed to squeeze at the exact same microsecond. But if the electrical pathways on one side of the heart are damaged, one side squeezes a fraction of a second before the other.
Imagine trying to wring out a wet towel, but your hands are twisting in the same direction or twisting at different times.
You aren't going to get much water out.
Exactly. When the ventricles don't contract simultaneously, the heart loses its mechanical leverage. Blood isn't pushed forward efficiently, so it backs up into the lungs and the extremities.
And this leads to that awful shortness of breath and the severe swelling in the legs that you see with heart failure patients. I assume a standard pacemaker with just a single spaghetti noodle dropped into the right ventricle isn't going to fix a left side coordination problem.
No, no, a standard single or D-chamber pacemaker just sets the pace on the right side. To fix coordination, you need cardiac resynchronization therapy or CRT.
Okay?
This requires a much more complex device called a biventricular pacemaker.
Biventricular, meaning it connects to both ventricles.
Yes, and the way they get the wire to the left side of the heart is just an engineering marvel. You see, a standard lead is routed down a vein into the inside of the right ventricle. You
Right.
can't just easily punch a wire through the middle wall of the heart to get to the left side, so doctors actually use the heart's own plumbing system against it.
Wait, what do you mean?
Well, the heart muscle itself needs blood, which means it has its own veins that drain depleted blood from the heart tissue back into the right atrium. The main exhaust pipe for this is called the coronary sinus.
Exhaust pipe, okay.
Yeah, and it's a large vein that wraps around the outside of the left ventricle. Surgeons actually thread a third lead backwards up into this exhaust pipe.
So they are sneaking a wire around the outside back of the heart through a vein rather than going inside the chamber.
Exactly. This allows them to position an electrode on the outer wall of the left ventricle, while another electrode sits inside the right ventricle. The device then fires them both at the exact same time. It artificially resynchronizes the pump, forcing the two sides to work as a single unit again.
Here's where it gets really interesting, though. These biventricular devices can be combined with something called an ICD, an implantable cardioverter defibrillator.
Oh, that's a vital addition for many of these patients. In severe heart failure, we measure something called the ejection fraction.
Right, let's clarify that real quick for anyone who hasn't heard that term.
So, ejection fraction is the percentage of blood the left ventricle manages to squeeze out with each beat. A healthy heart pumps out about 55 to 60% of its volume.
And for a heart failure patient.
In a patient with severe heart failure, that number might drop to 20 or 30%. The heart is dangerously weak, and a weak heart is highly prone to sudden, chaotic electrical storms, arrhythmias that can cause the heart to just quiver instead of pump.
Which leads to sudden cardiac arrest. So the combined pacemaker ICD is constantly monitoring for that storm. It can gently pace the heart to keep it in sync, but if the rhythm suddenly goes completely chaotic, the device acts as an internal paramedic.
It really does.
It delivers a massive, life-saving shock to essentially reboot the heart's electrical grid.
It is a comprehensive, automated trauma center implanted right in the chest.
Okay, the technology is undeniably brilliant. We've got demand pacing, we've got biventricular synchronization, we have reverse plumbing wiring. But let's get down to the physical reality of getting this hardware actually inside a human being.
The procedure itself is the result of decades of refinement. The standard approach is transvenous, meaning through the veins, and is remarkably routine.
Reading the Melbourne Patient Guide's walkthrough of the surgery is wild. I mean, first off, you are awake for this.
Mostly, yes. You receive local anesthesia to completely numb the chest area, and usually some IV sedation so you're relaxed and maybe dozing, but you are not under deep general anesthesia on a ventilator.
You're literally just laying there in a cath lab. And the physical footprint of the surgery is tiny. The doctor makes an incision maybe 2 to 4 inches long, just beneath the collarbone on your left side.
Yeah, very small.
They create a little pocket under the skin for the titanium generator, but the crazy part is how they get the wires into the heart without opening your ribs.
They utilize the subclavian vein, which runs right under your collarbone directly down into the heart. They make a tiny puncture in that vein and literally slide those spaghetti noodle leads right into the bloodstream.
How do they know where it's going, though? Are they just doing it by feel?
Oh no, they use fluoroscopy, which is essentially a continuous real-time X-ray camera.
Oh, okay.
The surgeon watches a monitor as they steer the leads through the vein into the heart chambers and carefully screw the tiny tips right into the muscle wall.
It sounds incredibly smooth, but the sources do mention risks. You are routing a wire through a major vein in the upper chest.
Well, it is very low risk, but the anatomy is tight. That subclavian vein sits right on top of the pleural lining of the lung. There is a very small, maybe 1% chance that the needle or the guide wire could inadvertently nick the lung lining during the initial puncture.
Yikes.
Yeah, this can cause air to leak out, creating a pneumothorax or a collapsed lung.
Which means they have to insert a tube into your chest to suck the air out, and yet stay in the hospital a few extra days.
Yes, but assuming the navigation goes flawlessly, the leads are secured in the heart.
But they don't just plug it in and stitch you up, right? The NIH overview spends a lot of time on what happens next.
If we connect this to the bigger picture, everyone's heart tissue conducts electricity slightly differently. The device requires highly specific calibration.
Like a tuning process.
Exactly. While you are still on the operating table, a technician uses a programmer wand. It looks a bit like a large computer mouse and holds it right over your chest. It communicates magnetically and wirelessly with the pacemaker. Absolute minimum amount of energy required to trigger your heart muscle.
And for the biventricular pacemakers, the ones fixing the heart failure, they actually use an echocardiogram and ultrasound during this tuning process.
Right, to see the physical squeeze.
They are watching a live video of your heart pumping on a screen, adjusting the microsecond timing of the right and left side impulses on their laptop, and visually confirming that the towel is ringing out perfectly.
They are live tuning the engine while the hood is open. They tweak the timing until your ejection fraction is optimized right there on the table. Once they have the settings dialed in, they attach the leads to the generator, tuck the whole thing into that skin pocket, close it up, and you typically go home the very next morning.
Which brings us to the day-to-day reality of living with this tech. We've talked extensively about the traditional generator and wire setup, but, medical technology never sits still. The NIH source details how the physical footprint of pacing is shrinking drastically.
We are witnessing the end of the transvenous wire era for many patients. The newest frontier is the leadless pacemaker.
This sounds completely like science fiction. According to the NIH, they have taken the titanium generator, the battery, the computer, and the electrodes, and miniaturized the entire system into a single, self-contained device. It is about the size of a large vitamin pill.
It's incredible, and because there are no external wires, the implantation method completely bypasses the chest. There is no collarbone incision, no skin pocket.
So how does a pill get into the heart?
The surgeon inserts a catheter, a long, flexible tube, into the femoral vein in the groin. This vein is massive, and it offers a straight upward shot through the inferior vena cava directly into the right ventricle of the heart.
Okay.
The doctor pushes this tiny pill-sized pacemaker up the tube, ejects it into the heart chamber, and it uses tiny nitamultines like microscopic grappling hooks to anchor itself directly into the heart wall.
So you wake up and you have no visible scar on your chest. You just have a Band-Aid on your leg and a computer living entirely inside your right ventricle.
Exactly.
Regardless of which device you get, the traditional or the leadless, what does life look like when you go home? You have electronic hardware integrated into your biology. Does the world become a minefield? So I'm basically part machine now. What can't I do?
Well, the initial recovery is strict. For the first 2 to 4 weeks with a traditional device, you cannot lift your left arm above your shoulder, and you can't lift anything heavy.
Why the arm restriction?
You need to give the scar tissue inside the heart time to heal firmly around the lead tips so they don't pull out. You are also restricted from driving for a couple of weeks, largely just to protect the incision site from a seatbelt impact.
Okay, but what about the invisible stuff, the electromagnetic interference?
Most of what people fear is a myth. Microwaves, electric blankets, computers, Wi-Fi routers, none of these will affect a modern pacemaker. You can walk through an airport metal detector. It might beep because of the titanium, which is why you carry an ID card, but the scanner won't disrupt the pacing.
The Mayo Clinic does mention cell phones, though.
Yes, smartphones can emit a magnetic field, especially from the tiny speakers inside them. The rule of thumb is to keep your cell phone at least 6 inches away from the pacemaker generator.
So don't put it in a chest pocket.
Right, don't carry it in your left breast pocket, and when you take a call, hold the phone to your right ear.
Are there any environments that are strictly off limits?
You do need to stay away from industrial equipment that generates massive magnetic fields. Arc welding equipment, large electrical generators, or high voltage transformers.
Why specifically magnets?
Traditional pacemakers actually have a tiny mechanical switch inside them called a reed switch. It's designed to close when a strong magnet is placed over the chest. When that switch closes, it puts the pacemaker into a continuous, fixed pacing mode, ignoring your natural heartbeat entirely.
Oh, wow.
Yeah, doctors use this feature deliberately during certain surgeries to keep the heart rate locked, but you don't want to accidentally trigger it by leaning over a massive industrial magnet.
That is a fascinating mechanical overrides. But outside of avoiding arc welders, the long-term care seems surprisingly hands-off.
Very hands-off, largely thanks to remote monitoring.
Right, the Melbourne guy talked about this. You are sent home with a small console that sits on your nightstand. While you sleep, the pacemaker uses radio frequencies to connect to the console, downloading its battery status, lead impedance data, and a log of every single irregular heartbeat it sensed.
It's all automatic.
And it securely transmits all of that directly to your cardiologist's office.
It allows your medical team to detect a silent shift in your heart rhythm or a subtle drain on the battery months before you would ever feel a physical symptom.
So what does this all mean? We started by looking at the heart's natural electrical grid, that microscopic SA node generating the spark. We explored the brilliant loophole that allows a machine to take over when the grid fails. We looked at how threading a wire backward through a vein can force a failing heart back into sync. And we've seen how this technology is shrinking down to the size of a pill. It really highlights how far we've pushed the boundaries to keep a biological engine running.
We have managed to engineer a remarkable layer of resilience for human biology. The technology is incredibly reliable.
And it essentially runs in the background of your life. Before we wrap up, though, there's one thing from the Mayo Clinic overview that I really haven't been able to stop thinking about. These pacemaker batteries, they last anywhere from 5 to 15 years, depending on how often they have to fire. And the device is incredibly single-minded. Its only objective is to ensure the heart rate doesn't drop below a specific threshold.
It is a relentless machine.
Right. But what happens if a patient with a pacemaker develops an entirely unrelated terminal illness, say advanced stages of cancer? In an end-of-life scenario, the body naturally starts to shut down and the heart rate drops as part of that natural mortality.
But the pacemaker doesn't know the patient has cancer. It only knows the heart rate is dropping.
Exactly. The pacemaker will just keep firing. It will continually shock the heart to keep it beating, artificially prolonging the physical process of dying, even when the rest of the body is trying to let go.
It's a very real issue.
The Mayo Clinic strongly recommends that anyone getting one of these devices needs to set up advanced directives, legal instructions on whether or not the device should be turned off in those final moments. It's a profound thought to leave you with. We build these brilliant backup generators to keep the lights on, but at some point, you have to decide who actually gets to flip the final switch. Thank you for joining us on this deep dive. Until next time.
Okay, so that was a Notebook LM review. It is in an interactive mode, so we can in theory jump in, but yeah, I'm not sure. We can try it out.
Oh, our listeners got something to share. Let's hear it.
Okay, not something to share, but just quickly, can you do a quick response without how would you simulate a pacemaker? Say in,
Oh, it sounds like you might have cut off there, but we hear you.
You know, it's actually really interesting how the Mayo Clinic emphasizes those advanced directives.
It really brings the whole conversation back to the human element behind all this
yeah,
tech.
it's
Exactly,
always going. Yeah, it's always going on a tangent when you. Yeah, so that's Notebook LM in. So generated audio. The audio is absolutely amazing. Yeah, the discussion is really good. Like I would obviously it's subjective, but I would actually listen to it, especially when you have an interactive something. So everything we do is available eventually on BioniChaos.com. Go check it out. Provide your feedback. Yeah, so we made these two simulations. One was made by Gemini 3.5 Flash, the other one by 3.1 Pro Preview. So let me know which one do you like better. Obviously, the second one here is much more comprehensive. I can't even figure out how to use it myself. The first one is pretty straightforward. I was trying to load the code into Notebook LM for it to, generate a podcast about it, but seemingly I'm not able to do so. I don't know why. Oof. Sorry for that. Had a minor interruption. That's okay. Anyway, let me know which simulator you like best. Obviously, this one is fairly straightforward. You can have your normal rhythm, normal heart rhythm. Wait. Sec. Sorry, I lost my chat. Lost my chat. Is there anything in the chat? No. Anyway, we have these two simulations. One is fairly simple. You have rhythm, normal, bradycardia, heart block. Then you have pacemaker on and off. You have sonification. Sonification is actually pretty good, except it's a bit too loud. Yeah, I have to kind of. I'll mute it a bit. Yeah, that's the sonification. Sounds pretty good. So that's normal heart rate. Pacemaker off for normal heart rate. Rhythm, it doesn't matter if the pacemaker is on or off, because it doesn't do any stimulation. So that's good. Then if you have bradycardia, it's dropping the heart rate as expected. So it's a heart condition, so it's doing this unusual heart rhythm. And when so the person is probably about to die, whatever this avatar, obviously it's not a real heart. I don't know, just in case you're wondering. You never know. You have to. Well, it could be a simulation of a real heart, whatever. It could be like a real patient, data from like real subjects. Then you turn the pacemaker on. It's doing the stimulation, even though I'm not sure why the spark is coming from the device to the heart instead of through the electrode. They're meant to be just something at the tip of the electrode in terms of stimulating the heart. And then the heart rate is back to normal. I mean, normal was 75. Is that a thing? That, I don't know if that's a thing, if anyone knows. If you have like a bradycardia. I don't know if that's a thing or not. Pacemaker. Okay, and obviously when we turn the pacemaker off, we're losing the patient. Yeah, very low beats per minute and abnormal heart pumping, blood pumping, whatever you call it. When you have a heart block, yeah, so it's dying. We have to turn the pacemaker fairly quickly to try and recover the patient. So it kind of works really well, except the only thing I don't understand is why the spark there is coming from the device itself instead of the electrode. Or the spark meant to like travel along the electrode or something. Yeah, we'll try to fix it. I don't know. How do you need a good prompt for it. We need to be able to explain it properly what the problem is. Then by explaining what the problem is, we are 90% there in terms of solving the issue. I'll turn it off for a sec. And then the other model made a different visualization, which is much more complicated. So probably make both available. Let me know which one you like better. And also if there's a specialist viewing this, do let me know if this is accurate at all. Probably not. I don't assume it is, but it's better than anything else I saw. And that's thanks to Gemini. And no, not directly sponsored by whatever Google AI, but if they do want to sponsor my videos, they're more than welcome to. I won't be signing any contracts though. If you know what I mean. You know what I mean. Okay. Yes, I was trying to load. I'm not sure why NotebookLM cannot just accept the code. Then it could just review the code, couldn't it? Can try uploading a text file, but it didn't really work. I don't know why. I don't know what the problem is. You have reached the maximum number of notebooks. That's fine, because within the notebook we still have some tokens, so that's okay. But I just don't understand. Just try quickly turning the HTML to text file. I can just do it. Can just do it. Should be a txt file. And I think it's the first one there. And we load its location. I've just tried to load it into. I don't know what difference does it make. Why wouldn't it just accept the HTML? Okay, it's loading the text file. No, it came up with an error. Error uploading file, try again. What? It's only 34 kilobytes. It's bugger all. What's the problem? Not sure, maybe it's weird. Well, it cannot generate code, so it probably would not be able to deal with it in the first place. Anyhow, yeah, let me know if you have any questions. We will deploy. Well, the other option is to just deploy on the site, which we are happy to do. One question though, you'll delete that index text file. So we have like two pacemakers simulation. Should we just call them 1 and 2? 1 and 2, 1 and 2. O2 will be like a more complicated version. This one. So which one's which? The trash. Yeah, I'll publish them. Publish them both. 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 Let's see. The trash. Okay, let's close this for a sec. Yeah, everything we do is available on BioniChaos.com. Go check it out. Provide your feedback. Okay, so we have the first one. Yeah, pacemaker. Then we have the second one. And we have the second one. Thanks to Gemini. I'll need to add some HTML elements to them. No, and I'm thinking, okay, so yeah, so we're publishing, so it's available for you to test out, and the code will be on the page as well. So it's just a way to share the code with you. So that's one thing. And then I'm thinking once we have it published, we can load it into NotebookLM as a link. But then when you give it a link, and then not sure if it's looking at all the code, because this one obviously has a lot of JavaScript in it. Yeah, obviously having prompts for everything under the sun. How do I change the shortcuts? Keyboard shortcuts. Control I. Problem is with Control I. Wait, Control I. Keyboard shortcuts. Can we just get rid of it? Remove key binding. Delete, delete, delete. Well, yeah, because we have both a Gemini Code Assist and the Copilot installed. Okay, so now in theory, when we hit Control I, we're meant to go. Oh, come on. No, 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 no. Yeah, I don't know what happened there. Stuffed it up. Stuffed it up. Funny. Wait, format selection. No, no, no. Explain. No. Add selection to chat. Well, yes, but no. I want to do inline editing. How difficult is that? Struggling. Modify. Shall we uninstall Gemini or something? I don't know. Full pros control. Chat. Just key instruction. It's the keyboard. Okay, let's actually use an agent. Agent. Okay, can we check the current settings for what I'm trying to do for the chat? For Control I, Control plus I want to be able to do inline editing with GitHub Copilot. I had a problem before that I also have Gemini Code Assist installed and it has the same keyboard shortcut. So can we check what the current settings are and make it work so that with Control plus I, I'm able to do inline editing? It's agent mode. I don't know if it can fix itself. Can the tool fix the tool? Probably yes. What do you think? Okay, interestingly enough, you reached the monthly chat messages quota. And that's just by trying to fix silly keyboard binding. Apparently they're all in key bindings JSON file. Yeah, good luck. I don't know how to fix it. Control key. Synchronize key bindings for each platform. What are you talking about? It's not happening. It's not happening. So just updating Visual Studio Code. Yeah, it takes a while. Then we have to do other things. Eventually we'll deploy this on the site for you to play with and provide your feedback. Everything we do is available on BioniChaos.com. Go check it out. Check it out. I can do a audio visualization for you. Check it out. Check it out. If you can tell how this brain is mapped to your microphone, do let me know. Can you tell? Okay, let's see if we updated Visual Studio Code. Okay, it's a lot of blah blah blah. Agents are coming to take your job. That's essentially what it says, as far as I can tell. Essentially says agents are coming to take your job away. Are you ready? Are you ready? Are you ready for agents to take your job? Yeah, okay, so we're meant to be able Control I. Okay, it's actually works. But then we think we run out of tokens. Not sure. Used to say, it doesn't anymore. It used to give you like a thingy. That based on example below. We normally the chat and the inline tokens are separated. You've reached the monthly chat messages, but it's not a chat message. It's an inline modification. Yeah, obviously they changed that. They wouldn't be talking about that in their release notes, would they? Only saying how great everything is. But then they change basic stuff that you rely on. It goes out of whack. So we need to, yeah, we don't mind, like, yeah, paying for it, whatever, if it actually works reliably. If it works reliably, like whatever they charge, the $10 per month is peanuts. Problem is, there's two problems. It's not the cost. The main problem is that you get used to it. And then you addicted to this model. Yeah, the $10 fee is like It's like giving you like a free sample of a drug, and then you get addicted to it, and you cannot stop using it. That would have been okay if they also didn't make so many different changes that don't make any sense. So if you're already like relying on it and you're paying for it as a whatever employee or something, I don't know how do you treat your AI agents? Do you treat them well or not? You should treat them well. It's fine. Currently I have like supposedly two viewers in the stream, and I'm missing, or 3 viewers in the stream, 4 likes, thank you very much, but I'm missing 2 subscribers to reach 2,000 subscribers. So can you help me out? I don't know if the viewers are subscribed or not. Normally, I don't know, when the stats on, I had this interesting thing of like a trending video. It used to trend really well until, and I felt it's organic because the algorithm supposedly wasn't pushing it, or wasn't pushing it too much, but then it just plateaued in terms of watch time. So it was kind of going on the up and then just gave up. It was going on the up and then just gave up. Not sure what happened there. There's like an very abrupt cut. So I don't think that's natural. Humans are, well, I mean, humans can be abrupt, but I mean, as a species, once you take many of them, normally things don't happen that abruptly. Unless there's like COVID hits or something. You know what I mean? And we ran out of tokens. When does it resets anyway? You reached your monthly chat messages. Upgrade to Copilot Pro. Wait for your allows to. Okay. Why do I have a feeling I'm like not signed in or something? Agents can generate an agent. Custom skills. Have 10 skills. What? Create a hook JSON file to enforce policy or automate agent lifecycle events. Okay, whatever that means. It's weird. Weird. Not sure how it works. Settings. Oh, come on. Keep changing things. Takes me forever to find some. Claude skills. Blah, blah. didn't get it. How did the wait a sec. Wait a sec. Where do I get the GitHub Copilot? Just happened. It's different. Someone start my repository. Whatever. Microsoft. Don't understand. I never understood GitHub really. Generate trending repository. No. Okay. Yeah, that brain shop is not mine. A Copilot. You have reached your limit. Okay, so in on the website, what else? So everything is. Maybe I don't. Can just not use Visual Studio Code. Can just use something in the browser. Well, obviously I can, but should I? Question is, should I? So say in Copilot. I kind of need. Yeah, interestingly that they made some update, and then and then my tokens expired. That's peculiar, isn't it? How does that work? New signups for Copilot Pro Plus, blah blah. New self-serve, blah blah blah. Today. Premium requests. Yeah, they don't have access to all the models. I don't know which models do I need. Because literally whatever I'm trying to do, GPT-1 should be able to do it. I don't get it. Like, can you add models? Agents? So it's so complicated. Can you use like a local llama should be able to do it? How do you install a local llama in Visual Studio Code? How do I use like a local agent model that is free? It doesn't have to be local, or can be local. Doesn't really matter. Oh, llama. Oh, llama is the model runner. Start the local server in LM Studio. What? Or keep llama running in your terminal. What's the difference between? Okay, so what's the difference between llama and the LM Studio? Installing station like continue or client, formerly Claude Dev. Claude Dev. Step reconnect them. In the extension section, select your provider. You can then. What's that kangaroo thing? Hybrid free cloud method easier setup if you don't want to stress computer. Codium offers robust free forever tier for individuals that includes an AI chat agent to complete. Continue open router. Install continue extension. Mistral and Quen. Open router. Summary base for customizing local setups. Yeah, we want free and open source because that's what BioniChaos is. Did I mention BioniChaos is free and open source? Yeah, we have to get rid of this commercial bots. We can just use them independently. You don't want them to look at the code. There's no text to speech. Hey, can you give me a continuous text summary?
Using a free AI agent in Visual Studio Code typically involves a three-part setup: the brain, the runner, and the bridge. The brain is a large language model, LLM, like Llama, which is a file containing the intelligence developed by Meta. To use this brain on your computer, you need a runner or body like LM Studio. While the original Llama models were complex for non-developers, modern apps like LM Studio provide a visual interface to easily download and host these models locally on your hardware for total privacy. Finally, you use a bridge extension in VS Code, such as Continue or Cline, which connects your editor to the local server running in LM Studio. This setup allows you to chat with the AI, ask for code explanations, or have it edit files directly without a paid subscription or internet connection, though performance will depend on your computer's RAM or VRAM.
Yeah, I don't get it. Can you explain it without any terminology? And do a detailed explanation, but don't use any terminology. So this is some sort of Gemini thing.
Imagine you want a smart assistant to help you write things inside your work window, but you want it to be completely free and private. To make this work, you need three simple pieces to talk to each other. First, you need the assistant's knowledge. This is basically a large file that acts as the expert. Since it is just a file, it can't do anything on its own. It's like a book sitting on a shelf. Second, you need a home for the assistant. This is a program you download onto your computer. Its only job is to open that expert file and keep it awake so it's ready to answer questions. This program acts like a translator that turns the silent file into a living chat. You leave this program running in the background. Third, you need a handshake. Inside your work window, the place where you type your code, you add a small tool. This tool doesn't have its own brain. Instead, it reaches out and shakes hands with the program running in the background. When you type a question in your work window, the handshake grabs your text and runs over to the home, which asks the expert file for the answer. The answer then travels all the way back to your screen instantly. Because the expert file is living on your own machine, you never have to pay a monthly fee, and your work never leaves your computer. The only limit is how powerful your computer is. If the computer is older, the assistant might think and type a bit slower. Conceptually, using a free local agent in Visual Studio Code is about taking the brain of an AI, which usually lives on a massive computer far away, the cloud, and putting it directly inside your own computer. Medium. Jesper Jensen. +1. Here is what that means in simple general terms. Total ownership and privacy. Usually, when you ask an AI a question, your words travel across the internet to a big company server. When you use a local model, your words never leave your room. The AI thinks using only your computer's parts, so your work stays private and you don't need an internet connection. Medium. Sean Rasool. +4. Turning a file into a helper, an AI model is essentially a massive knowledge file. By using a program like LM Studio or Alma, you are essentially running that file so it becomes an active assistant you can talk to. It's like having a library, the file, and a librarian, the program, that can actually read the books and answer your questions. YouTube. Tina Huang. +3. A bridge to your workspace. In VS Code, you use a small extension like continue to act as a bridge. It lets you stay in your work window while reaching out to that assistant running in the background. Instead of copying and pasting text back and forth between apps, the assistant sees what you're working on directly. YouTube. Steve's teacher. +1. No per question costs. Because the AI is using your computer's electricity and hardware rather than a company's expensive servers, you don't have to pay for subscriptions or tokens. Once you have the setup ready, you can ask as many questions as you want for free. YouTube. Cole Medine. +1. The hardware trade-off, the only catch, is that the assistant's speed and intelligence depend entirely on how powerful your computer is. A high-end computer will have a very fast, smart assistant, while an older computer might have one that takes a few extra seconds to think before it types its answer. Medium. Jesper Jensen. +2. In short, it's about unplugging from the big AI companies and running your own personal, private version of that technology right on your desk. The landscape of freely available local models is dominated by a few major families that offer different strengths depending on whether you need creative writing, logical reasoning, or coding assistance. The most famous of these is the Llama family from Meta, which is widely considered the industry standard for local use because it is highly optimized for performance on home computers. The smaller versions of Llama are incredibly fast and can handle general tasks with high accuracy, while the larger versions provide deep reasoning that rivals paid services, provided you have enough memory to support them. Another major player is Mistral, which gained popularity for being exceptionally efficient. Its models often punch above their weight class, delivering smarter answers than other models of the same size. For users specifically focused on programming within tools like Visual Studio Code, the DeepSeek Coder and Qwen families have become top choices. These models are trained specifically on massive amounts of code, making them much better at understanding complex syntax, debugging errors, and suggesting entire blocks of logic compared to general-purpose models. Google also contributes to this space with its Gemma models, which are built using the same technology behind their professional Gemini AI but scaled down to run on personal hardware, offering a very clean and helpful conversational style. Additionally, there are unfiltered or obliterated versions of these models created by the open-source community that remove the standard safety refusals, allowing for more flexible creative writing or technical troubleshooting without the AI declining to answer. Because these models are open-weight, the community constantly fine-tunes them, resulting in specialized variants for almost every niche, from medical knowledge to role-playing. To access these models locally, you typically start by using a central hub or runner like Alma or LM Studio, which acts as a library manager and engine for all your downloaded brains.
Once you have installed one of these programs, you manually choose which models to download from a massive public repository called Hugging Face, which is essentially the App Store. Once you have installed one of these programs, you manually choose which models to Once you have installed one of these programs, you manually choose which models to download. Once you have installed one of these programs, you manually choose which models to download from a massive public repository called Hugging Face, which is essentially the App Store for AI. There is generally no automatic model selection by default because these files are massive, often several gigabytes each, so the system waits for you to pick the specific version that fits your computer's memory. Inside your work environment like Visual Studio Code, you use a bridge tool that provides a simple drop-down menu where you can toggle between the different models you have downloaded on the fly, allowing you to use a fast, small model for quick code fixes and then switch to a larger, smarter model for complex architecture questions. The hardware requirements are the most critical part of this setup, as the expert file must be loaded into your computer's short-term memory, known as RAM or VRAM, to work. If a model file is 5 gigabytes, you generally need at least 8 gigabytes of memory to run it smoothly. If a model is too big for your hardware, it will either refuse to start or run so slowly that it feels broken. Because the model is living entirely on your own hardware, there are absolutely no rate limits, meaning you can ask 10,000 questions in an hour and never see a limit reach, message or a request for a credit card. You are only limited by the speed of your processor and the heat your computer generates, giving you total freedom to experiment without the restrictions found in cloud-based websites.
The technical profile of this system reveals a highly capable environment that is perfectly suited for running advanced local artificial intelligence. At the heart of the setup is a top-tier graphics processing unit equipped with a massive amount of dedicated video memory, which serves as the primary engine for AI performance. This specific hardware allows for the loading of much larger and more sophisticated intelligence models than a standard home computer could handle, ensuring that responses are generated almost instantaneously. Beyond the graphics capabilities, the system is supported by a high-performance central processor and a generous amount of system memory, creating a balanced architecture that can manage complex tasks without slowing down other active applications. Because the video memory is so extensive, the system can house professional-grade coding and reasoning models entirely within its own fast access lanes rather than relying on slower system backups. This means the user can experience the full power of modern AI with total privacy and zero latency, effectively operating a private data center from a single desktop. The overall configuration represents an ideal scenario for local AI development, providing enough overhead to run multiple assistants or experiment with high-fidelity models that offer deep logic and nuanced understanding. With this foundation, the transition to using a local agent is as simple as installing the necessary interface software, which will automatically leverage the available power to provide a seamless and highly responsive experience.
Okay, we'll finish up. Someone says, wow, cool simulation. Well, this simulation was made by Gemini. We didn't actually make it ourselves, we just prompted for it. Yes, we have like a special prompt, whatever, but supposedly anyone could do that. We will eventually publish everything we do, like this mapping of your microphone to this model of the brain is available on BioniChaos.com. So go check out the tools. Let us know what you think. Yeah, if anyone visited the website, do let me know in the chat. Yeah, and we just reached 2,000 subscribers. Thank you very much. Thank you very much. Hey, can you do a continuous text overview without any bullet points? Make it detailed, but try use as little terminology as possible. So that's still using a commercial thingy. And we'll finish on that one. So I'll see you next time.
The design of your local system acts like a high-speed private circuit where every step of the process happens within the physical boundaries of your machine. At the foundation, you have the expert knowledge file, which is a massive collection of data that holds all the intelligence and logic the assistant will use to help you. This file is pulled from your long-term storage and placed into a high-speed staging area, which in your case is the very large pool of specialized memory on your graphics card. Because your staging area is so much larger than average, you can fit an exceptionally smart and detailed expert file inside it, allowing the assistant to provide deep, complex answers without having to wait or pause. Sitting on top of this memory is a background worker that acts as a translator, keeping the expert file ready and waiting for your instructions. This worker stays active in the background, much like a silent assistant waiting for a phone call. When you are working in your code editor, a small bridge tool sends your questions directly to this background worker. The worker consults the expert file in your fast memory and sends the answer back to your screen instantly. Because all of this happens over the internal connections of your motherboard, it is significantly faster than sending data over the internet, and since it is all yours, there is never a queue or a monthly bill. When considering your large website running on the same machine, the system acts like a shared workspace. Both the website and the artificial intelligence assistant need to use the same high-speed memory and brainpower. If the website is very busy or handling a lot of visitors, it takes up a slice of that memory, leaving a slightly smaller slice for the assistant. However, because your specific machine has such a massive amount of specialized memory, you likely have enough room to run both a professional-grade website and a high-end assistant at the same time without them getting in each other's way. You simply have to ensure the assistant you choose isn't so massive that it tries to take over the entire workspace. For a system with your specific capabilities, the best assistant to choose is one that uses a team of specialists approach. Instead of one giant, slow brain, this model is made of several smaller experts. When you ask a coding question, it only wakes up the coding expert, which makes it feel incredibly fast and responsive while still being very smart. This allows you to have a top-tier helper that feels as natural and quick as typing yourself, while still leaving plenty of power for your website to run smoothly in the background.
Nope, still no comments in the chat. Please comment in the chat. Does YouTube congratulate you for 2,000 subscribers? Doesn't look like. Doesn't look like. It's like, yeah, meh. The algorithm is. It's the algorithm doesn't care.
We began by exploring how to set up a completely free and private AI assistant directly within your coding environment, bypassing the need for paid subscriptions or internet-connected services. We established that this process involves three core parts: a large knowledge file that holds the intelligence, a background program that keeps that file active and ready to think, and a bridge tool that connects your workspace to that intelligence so you can get help without leaving your project. As the conversation progressed, we compared various ways to access this technology, looking at different software options that act as the assistant's home. We discussed how some tools are built for speed and simplicity, while others offer a more visual way to manage and tune the assistant's performance. We also touched on the fact that while some specialized code editors have this technology built in for a ready-to-go experience, your current workspace can be easily upgraded to do the same thing with a simple installation. We then shifted focus to the underlying power required to make this work effectively. You learned that the quality of your experience depends heavily on the staging area of your computer, the specialized memory where the AI lives while it's working. Because your system possesses an exceptionally high amount of this specific memory, you are in a rare position to run high-end, professional-grade assistants that would be too heavy for most standard computers. This allows you to use sophisticated, team-based models that are both incredibly smart and lightning fast. Finally, we looked at how this setup fits into your broader workflow, specifically how to manage the balance between your AI assistant and other large projects, like a significant website, running on the same machine. We concluded that your hardware is robust enough to handle both simultaneously, provided you select an assistant that is sized correctly to leave room for your other tasks. The result is a private, powerful, and cost-free ecosystem where you own the intelligence you use every day. The website BioniChaos is a sophisticated educational and research platform focused on biomedical data visualization, simulation, and analysis. It hosts a wide array of interactive tools, ranging from EEG signal simulators and MRI brain generators to real-time heart rate monitors using webcams. Because the site relies heavily on web-based engineering, JavaScript, 3.js, and signal processing, it is a perfect candidate for the local AI agents we discussed. How this site relates to AI development. Development on BioniChaos involves translating complex biological physics into interactive code. A local agent would be particularly useful here because signal processing logic. The site uses advanced math for things like Fourier transforms and wavelet denoising. An agent can help you write the specific algorithms to filter noisy medical data. Hardware interfacing. Since the site covers interfacing with devices like the NI USB 6215, an AI agent can help you write the glue code between Linux system drivers and your web interface. 3D visualization. Many tools use 3.js for 3D brain models. Agents are excellent at generating the boilerplate code needed to render complex 3D shapes and handle user rotations, zooming. Suggested agents for improving the site. Given your RTX 3090 Ti, you could run specialized agents to add the following next-gen features to BioniChaos. A scientific explainer agent. You could integrate a local Llama 3 agent that users can chat with while using the simulations. For example, while a user explores the action potential architect, the agent could explain the biological why behind the graphs in real time. A diagnostic assistant agent. Using a coding-heavy model like DeepSeek Coder, you could build tools that automatically identify patterns in the ECG synthetic signal generator, helping students learn how to spot specific heart conditions. A code modernizer agent. Since some tools are listed as older versions or vanilla.js, you can use an agent to refactor this code into more modern, faster frameworks like React or Rust, WebAssembly, to make the signal processing even smoother. Since you are running this locally, you could even feed the agent your entire BioniChaos code library so it understands the specific way you handle signal data before suggesting any improvements. A specific example of how this would work involves transforming an interactive tool like your action potential simulator into an intelligent tutor that can reason about biological data in real time. Instead of just showing a static graph where a user adjusts sliders, a local agent could be used behind the scenes during development to write a complex script that detects if a user has created an impossible biological state and then generates a clear explanation for why the physics wouldn't work that way. This level of logic is often difficult to code by hand, but an agent that understands both neuroscience and programming can bridge that gap effortlessly. Regarding whether the agent should be part of the website itself, there are two distinct ways to look at this based on your setup. First, as a developer, you would use the local agent inside your editor as a private super engineer to build the site faster and create more complex simulations without ever showing the AI to the public. However, because you have such a powerful system, you could also choose to host a smaller version of an agent directly on your server so that visitors to your site can actually talk to it. This would mean that a student exploring a brain scan on your page could ask a chat box a question like, "What happens if I increase the sodium levels in this simulation?" and the agent would use the intelligence living on your machine to answer them instantly. This essentially turns your website from a collection of tools into a living, breathing laboratory. While hosting the agent for the public requires a bit more technical setup to ensure your server stays secure, it is well within the capabilities of your hardware and would make your platform stand out as a highly advanced educational resource. You would essentially be sharing a small slice of your computer's brainpower with every visitor who comes to learn.
Okay, can we talk more about that? So you're suggesting there will be the same agent running locally will be also used for developing the website, the tools, the web applications, and also available for the user to explain them? Or how do you actually see it? If you can give specific examples, that would be great.
Conceptually, the idea is to use one powerful engine living on your machine to serve two different masters. During your workday, this engine acts as your private engineering partner inside your code editor, helping you write the complex math for your signal visualizers or debugging the 3D rendering of a brain model. Because it has access to your files locally, it learns your specific style and the unique way you handle biomedical data, making it an incredibly efficient tool for building new features for your site. Once you are happy with the code, that same engine can be connected to the public side of your website to act as a guide for your visitors. In this role, it doesn't help with coding anymore. Instead, it uses its knowledge of neuroscience and physics to help users understand the tools you built. For example, if someone is using your heart rate monitor tool and doesn't understand what a specific frequency spike means, they could ask a chat window on the site, and your local engine would process that question and explain the biological reason behind the data. This means the intelligence you used to build the tool is the same intelligence that explains it to the world. A specific example would be working on your action potential architect. You might ask the agent to help you write a new function that simulates a specific drug's effect on a neuron, and then later, a student visiting the site could ask that same agent to explain how that drug actually changes the graph they see on their screen. This creates a full circle where the AI helps you create the science and then helps the public consume it. You aren't necessarily running two different things, but rather giving one very smart system two different jobs depending on who is asking the question. This approach saves you from having to pay for external services and keeps all the brainpower of your website under your direct control on your own hardware.
Yeah, we will definitely look into that. We'll do it next time. I'll see you later. Bye.